All right, let's go to page 57 when we're done. So this is just going to be a very short, mostly review of exponential functions, just kind of, hey, don't forget what these are, because they're not brand new to you, but then we're adding in some limit stuff, just kind of connecting it to some things that we know before we get deeper into them and start talking about transformations and all that good kind of stuff. All right, so in math, we study several different types of functions. The functions they show up in every math class from Algebra 1 to Calculus. The three families, so these are considered families because these are the parent functions right here, are also featured predominantly in the SAT and ACT. Okay, so you've got the linear parent function. That's an example of it. Well, actually, that's not the parent function because it would just be x, but in what it looks like, quadratic and exponential, okay? None of which are brand new to you. But what makes exponential exponential is not just that it has an exponent, because this one has an exponent as well, but that the exponent is the variable, or has the variable in it, right? Okay, so exponential functions are some of the most important functions in the real world. They appear in many places as population growth, money, which is interest and debt, which you will be very interested in when you start getting loans for things and paying off debt and getting into debt like most adults do. Radioactive decay, spread of disease, so you've used it in science and you've used it in math. In addition, the SAT will include several questions that require an understanding of exponential functions, so basic understanding here. All right, so here's some key characteristics. This is our general form, a times b to the x, and this form right here should look very familiar to what we've been doing with geometric sequences, right? So even though we had like the g sub k times r to the n minus k, then we put it in that formula, and then instead of having n minus 1, we changed it to just n, and got our, and then it was more like in this form. I mean, we had different variables, but basically in that form is what we were doing. Okay, where b is greater than 0. So b is not going to ever be negative, and we're going to talk about a being positive as well. Basically, a can't be 0. If a is negative, that means there's a reflection of the general form. And b cannot be 1, because if b is 1, then it doesn't matter what the exponent is, nothing's changing, right? And if a is 0, then the whole thing's 0 and nothing, it's not exponential, okay? So a represents our initial amount. Our initial amount, because remember when we put it in this form from the geometric sequence, if that was just n, that's like n minus 0, and that would be your a sub 0 term, which is your initial term, right? Or g sub 0, whatever. And then b represents the common ratio, which we can also talk about as the base. It's the base of the exponent, but it's the common ratio, and what, you know, it's both things, really. We have two basic scenarios, exponential growth and exponential decay. In both of these, a is greater than 0, okay, so it's got to be positive. For exponential growth, b is greater than 1, so 2, 3.57, whatever, greater than 1. For exponential decay, a is greater than 0, but b is between 0 and 1, so it's 1/2 or 0.3 or something like that, okay, but positive always. And increasing and decreasing. So the increasing, decreasing, concave up, concave down in behavior, that's all kind of stuff that we're adding to this. I'm sure you've talked about it with increasing and decreasing before, but probably not the others, and that's okay. But exponential functions are always increasing or always decreasing. They don't change. It's not going to change from increasing to decreasing or decreasing to increasing like a quadratic would. So they will never switch from one to the other, so they have no relative extrema. If I don't change from increasing to decreasing or vice versa, I can't have a maximum or a minimum. All right, so there's no maximum in here, none at all. Then as far as concave up and concave down, they are always concave up or always concave down. They will never switch, which means there is no points of inflection. Because remember, your point of inflection is where you change concavity. So if I look at exponential growth here, is this exponential growth increasing or decreasing? Increasing, and it's always increasing. And Is it concave up or concave down? Concave up, because your rate of change is increasing, right? Concave up. Okay. Exponential decay, increasing or decreasing? Decreasing. And is it concave up or concave down? Concave up, because my rate of change is increasing, right? Very good. Okay. Any questions about any of that? All right, so then let's talk about end behavior. For exponential functions in general form, and so your general form, remember, is the, well, here, we'll just write it right here, is f of x times a, oh, not times, I'm sorry, that's what it should be, equals a times b to the x. So we don't have any translations, right? We're not adding anything to the end or whatever. That's our general form. As the input values increase, so as x gets bigger and bigger and bigger, without bound, that means we're going to infinity, right? The output values will increase or decrease without bound, or will approach 0. Okay? So your only options for your end behavior limit statements. So notice all three of these limit statements say as x approaches either positive or negative infinity of a times b to the x. It either equals infinity, negative infinity, or 0. Now, if there was a translation and we moved it up or down, that could change the 0 part, but it wouldn't change the other part. So when we look at this one, as x approaches infinity, f of x is approaching infinity, right? Well, as x is approaching negative infinity, so if I'm putting numbers in here that are getting smaller and smaller and smaller, is there any x I can substitute in that would actually get me 0? I'm never going to actually get to 0, right? It's never going to be negative. So I have, what's this thing called down here? Horizontal asymptotes. So when we are approaching 0, that's because we have a horizontal asymptote. Right? We agree with that? So then on this one, as x approaches negative infinity, f of x is approaching infinity. And as x approaches infinity, f of x is approaching what? What's the graph approaching? 0. What questions you got? We all good? Okay. All right, so it says to write the limit statements for the end behavior. This doesn't have a name. We'll call this f of x. So the left end behavior, going to the left, and it is end behavior. We're ending, well, we don't really end because we're going to infinity, but this is the limit as x approaches negative infinity. So let's talk about how we write this real quick. I know it's harder to tell when it's written by hand, especially by my hand, but the LIM right underneath it is as x approaches negative infinity. And technically, like if it was typed up, then this part is usually little but like smaller font. I know you can't write it. I definitely can't write it that way up here. As long as you're making it, I just want to make sure you understand it's underneath it and not next to it, and there's no division sign or anything like that, okay? So the limit as x approaches negative infinity of f of x, so that's next to it, equals what? As x approaches negative infinity, what is f of x approaching? 0. Then the limit as x approaches infinity of f of x equals what? Infinity. We agree with that? All right. So that, oops, I guess I don't need to do that. Let's call this one h of x. We could call it f of x again. It doesn't really matter. But the limit as x approaches negative infinity. And how do I know that negative infinity goes first? Because it says left. And when you go to the left, you're going to negative infinity. Of h of x, and you always have to have an argument, okay? The limit of h of x equals what? Negative infinity. And then the limit as x approaches infinity of h of x is equal to what? 0. Okay. Everybody okay with that? All right, so now on C, they give us a function. They don't give us a graph. Well, those are functions too, but we have an equation here. So this right here, this is B, and this is what we need to look at. And for this one, B is between 0 and 1. So then is it growth or decay? If it's between 0 and 1, decay. So that makes this decay. So if I have a little sketch here, it generally looks like that. So since it generally looks like that, and I don't have any shifts here, then I can say that the limit as x approaches negative infinity of g of x is equal to what? Infinity. Good. And the limit as x approaches infinity of g of x equals what? 0. Everybody okay with that? So those should be very simple and basic to figure out. We got to make sure that we're writing them correctly. Any questions? All right. So then for each of the following, we're going to determine if the exponential function is increasing or decreasing and concave up or concave down. All right, so for A, is it concave up or concave down? Up, right? And the reason we know is our rate of change. We look at these little slopes here. Those are increasing, right? And then B, is the function itself increasing or decreasing? Decreasing. The y values are getting smaller. As x goes from left to right, the y values are decreasing. That's what we're looking for there. Okay. All right, concave up or concave down for B? Down. Because if you look at these little tangent lines here, the slopes of those are decreasing, right? They're getting more and more negative, so that's what makes it concave down. Is the function itself increasing or decreasing? Decreasing. We agree with that? Okay, so on C, here's B. In this case, B is greater than 1. So what does that make this? Growth. So I draw myself a quick little sketch there. Concave up or down? Up. Increasing or decreasing? Increasing. What questions do you have? Okay. All right, so then we have selected values of the function f are shown in the table, and we want to determine if f could be linear, quadratic, exponential, or none of these. So let's start by looking at our differences here. So this is 2, then 4, then 8, then 16. Okay, so is it linear? No. Okay. Now, if it is quadratic, then our second differences would be the same. Or we could look at our first differences, and if our first differences increase at a constant rate, that makes it quadratic. Do these increase at a constant rate? No, because it's 2 and then 4 and then 8, which is basically those differences, so it's also not quadratic, right? So then it's either exponential or none of these. So one of the ways we looked at whether or not it was exponential was we looked at the ratio, right? If I put 5 over 3, it should be the same as 9 over 5 and 17 over 9 and 33 over 17. Are those the same? No, okay? Because if I put 5 over 3, and then 9 over 5, I'd have to be able to reduce 9 over 5, and I can't. So I do not get a common ratio out of just these numbers here. But if you look at this right here, would that give me a common ratio? If I put 4 over 2, what am I going to get? 2. If I put 8 over 4, I get 2. If I put 16 over 8, I get 2, right? So I get a common ratio from my first differences. So we haven't looked at one of those like that because we were strictly looking at geometric sequences. But this is about exponential functions, which can come from geometric sequences. But because I had to do this first and then I get a common ratio, it does make it exponential. It's just exponential with a translation in it. All right? And then we'll figure out how to get the translations out of this a little bit later. But so because this part is geometric, since I get a geometric sequence here with a common ratio, that's what makes it exponential. Okay? And we're not going to worry about what the actual function is right now or anything, because that gets a little wacky with this one. But we okay with that? So one more way to kind of look at your data there. What questions you got? Oh, there's someone at the door. Where have you been? Oh, man. Okay. Are we good? Any questions? All right. I told y'all it was short and sweet.